Everybody, this is Dr. Dowd presenting HSC Pure Maths 1. Happy listening. The video is the beginning of a series through which I intend to exhibit exploits of HSC. Most especially for researchers and university engineering, physics, and mathematics students. I'll start off with mathematical induction. There are some questions with which I intend to illustrate some vital usefulness of this topic. As a way of reminder, mathematical induction is a method with which a mathematical statement is proved to be valid on finite or all natural numbers. Let's begin with the first one. This is a type of series that takes two numbers at the beginning and continue to iterate by increment with just one more number. So at the first instance, it's starting from 2, k equals to 2. It takes 2 and 3. All right. When k equals 2, this is what results. When k equals 3, that results. The sum will be equal to 8. And you can see 2 times 2 raised to power 2 is equal to 8. It means it agrees with the right-hand side. Again, when k equals 2, 3, 4, it has done an increment. Yeah. The product is, the sum is 24. And from the right-hand side, it is also 3 times 2 raised to power 3, which is equal to 24. Now, we assume it is true for the R case. And if it's true for the R case, this equation will be valid. We now consider the R plus 1 case. After considering the R plus 1 case, we add it to both the left and the right hand side of this expression. As we do so, we arrive here. And if we simplify the right hand side, the more we'll arrive here, which is valid if and only if M is equal to R plus 1. Okay. Second question. That has to do with the turn ratio. The trigonometric ratio. Now, this type of series is also the irregular type. The first expression that is not under summation is ever present. So if we iterate it with M equals 1, we are going to have this. It will be an instance in which I is equal to 1 under the summation. The first, and that will be this. Under simplification, it's this, and it ultimately will give that. And it tallies with the right-hand side in the instance at which M is equal to 1, as you can see. Now, for the second time, M is equal to 2. This is there. The instance at which I is equal to 1 is there. the instance at which I is equal to 2 will give this. We'll simplify again, and at the end of the day, we'll find it to be equal to this. And that tallies with the right hand side for m equals to. We assume it's true for the R case, and that's this. After which, we consider the R plus 1 case, which will bring us here. And this is the R case, our assumption. R plus 1 case will bring us here. We now simplify the right hand side. And at the end of the day, it will result into this, which indeed shows that it is valid for the instance at which m is equal to R plus 1. The identity we have utilized all through is this. Now, then this category of application will assist anybody who intends to study difference equation. Difference equation you meet in discrete modeling, time series, differential equations, or distribution theory, where you'll be thinking about u of n plus 1 minus u of n, or what have you. If you know a lot about this, that wouldn't be a problem at any instance. The next question, which is question 3, says we should show that this expression is a multiple of 7. If that is valid, then this is true. Where p is any natural number. In fact, k and p natural numbers. Then we just say that if it is true, this is true for k, then what about the next instance? The k plus 1 instance, where k plus 1 will be put in the office of k. And as you do so, you arrive here. You simplify that further, that brings you here. But here, if you make 2 raised to power k plus 2 the subject in this first equation, equation 1, you arrive here, and that simplifies to be this. As long as p and k are natural numbers, the quantity inside this bracket is a natural number. And that shows that that's indeed, the expression we're talking about is always a multiple of 7. Okay, the next one says, show that this is a multiple of 7 for some odd naturals. This is the generator of odd natural numbers. If r equals 1, it's equal to 1. If r equals 2, it is equal to 3. If r is equal to 3, is equal to 5. This is generating odd numbers. And if that statement is valid, then this must be true. The one I call equation 1. This is 8 raised to power 2r minus 1 plus 6 raised to power 2r minus 1 is equal to 7p for some naturals r and p. Now that's for r is. We will now consider the r plus 1 case. As we do so, we put r plus 1 in the office of r, and that's results. Simplify that further to get this. Now you can now make 8 raised to power 2r minus 1 the subject, and this will happen. Under simplification, it becomes this. And you can easily see that this is a multiple of 7. 7 divides this any day. Now, this is number 6. As for number 5, I think I want you to look at that at your leisure. It is very, very similar to the number 4 I've just seen. Now, it says show that either this or this is divisible by 11. Okay. If it is indeed true, then the product is obviously divisible by 11. And that's the product for some RP in naturals. Hence, this is the product of sum and difference. It's equal to the difference in squares. And that is our equation 1. Now, if we consider the next instance, put r plus 1 in the office of r, you arrive here. Under simplification, it takes you here. If you put 12 to power 2r, the subject here, you arrive here. And that simplifies to be this. And this indeed shows that 11 is, it's a multiple of 11. No, these are the kind of exploits that I will be illustrating here. More to come in additional series. Please like, share, and subscribe. Thanks for listening.